So some were asking about term tests, like when it's tentatively scheduled for, yeah? So, I consulted with Professor Evans, who taught this course last fall, yeah? So, and he permitted me to post his last fall term test on my Quercus page. Is it clear? It doesn't mean I will post it right away, so I will post it when I feel it would be appropriate. Okay? Come on in, please. So are you ready? Okay, so please turn the camera on. Yeah, so is it clear? Yeah, so I want to keep you busy, and a lot of additional stuff will be posted sometime next week. And my intention is to keep you busy during the reading week, really to make sure that you indeed read this stuff and work on problems, rather than enjoying sunshine somewhere in Florida. Okay? Keep in mind is that I'm not in position to post other instructions materials without their permission. Yeah? So anything that was created by Professor Evans belongs to him, so he possesses copyrights, but if it's okay, I can do it. Otherwise, I cannot. Okay? Now, the beginning of today's class meeting is a kind of bridge between what we studied during the first 3 weeks of this course and what will be next, and what you actually studied to some extent in B52. So specifically, we will start discussing cumulative distribution functions. Okay? So, not only in univariate, but in multivariate case. Sounds exciting, yeah? And recognize that you did see some multivariate probability theory in B52. So you heard about correlation, yes? So I teach B52 this semester, so I know the syllabus and I know what is being covered. But there are many differences in how it's covered in C62, and of course, I will address these differences and remind you what you are expected to remember from B52 as concerns multivariate probabilities. But you studied the bivariate normal distribution, I assume, so you heard about multinomial distribution. I'm not saying that these were your most favorite topics in B52, but that's what you are expected to remember, and that's what we are going to use and extend. Now, something about what you're expected to read. Yes, so when it's measure theory, so it's not that easy to find a good book for review. But I have some additional ideas on what might be useful for you to read. But for multivariate probability theory, there are several good books, and I'm going to mention them. Yes, so first of all, Gnedenka's book has nice stuff with good examples. So look at pages from 125 through 158, but there are also some exercises at the back of this chapter. So also Ross, a first course in probability. Sections 6.1 through 6.3 and 6.7 and other sections from chapter 6 if time permits. So, and from Evans and Rosenthal's book, so you can check sections 2.7, 2.8, and 2.9. Now, I do not specifically follow all topics from the chapters, and there is some stuff which is my own contribution, so I comment on this stuff. And I share my lecture notes with you. But this might be useful books for you to read, okay? And the final remark is that for the term test 1, it's going to be open book, so you will be able to bring your handwritten notes or some textbooks if you want, okay? But no electronic devices will be permitted, period, okay? So this information will also be posted. Yeah?
Can we bring the notes just printed?
Like if you have actually typed notes and printed, yeah, you may. So, but there should be hard copies. Okay. So, then I want to talk about some topics discussed briefly at the end of last Wednesday class meeting. So then I spoke about probability measure on the real line that is generated by specific random variable x. Yeah, so we discussed the Borel sigma field on R1, and then I introduced specific Borel sets on R1, which intervals from negative infinity to x inclusive, where x is fixed. So it's the fixed value of the argument, and probability that random variable x belongs to this Borel set on R1 is the same as probability that a random variable is less than or equal to x. And you know from B52 that this is nothing but your CDF of random variable capital X. Okay? then if B is interval from, oh, I'm sorry, if your Borel set B is interval from A to B, where B is included, then probability that your random variable is between A and B, so which is the same as probability that your random variable belongs to such a Borel set, is expressed as capital F sub capital X of B minus the CDF of this random variable evaluated at point A. Therefore, we could use the CDF to define the probability measure NR1, which is associated or generated by this random variable capital X. Is this clear? So the CDF is sufficient. Okay. Then this gives us what is known as Lebesgue-Stiltjes measure NR1. So in some books, including Billingsley, it's just called Stiltjes measure. Okay? And then what we will need to do is to find expectations of functions of random variables. Yeah? So when we need to find, say, expectation of a random variable, we need to integrate with respect to this measure. So, chapter 3 of Billingsley, and specifically section 17, gives you some idea how to do it, but also Gnedenko has a Stiltjes integral considered in the context of probability theory on pages from 147 to 153. And also he calls it a Stiltjes integral. Okay. So in Billingsley's book, it's more formal and condensed. It's more watered down. Yeah, so it's easier to read from Gnedenko's book. But what it does is it provides a unified approach to find expectations of discrete, absolutely continuous, and general random variables, okay? Because what you learned in B52 is that expectation of the discrete variable is the sum of x times P of x, where P of x is PMF. For absolutely continuous case, your expectation is the integral from negative to positive infinity of x times f of x dx, where f of x is your probability density function. So, but these formulas are obtained from special cases. What we really have here is that we integrate from negative infinity to positive infinity function x with respect to probability measure. And this probability measure is the one generated by the random variable x being considered. And how do we define the integrals? I'm not asking you how we evaluate the integrals. I'm asking you how do we define integrals in calculus? Yeah, so thank you. So it's a limit of integral sums. Yeah, so of course we need to prove that such limits exist and unique. So it's a lot of headache. So here, it's even more headache than in calculus, because our integrals are with respect to a certain probability measure. Okay? So, and I am asking you to read 6 pages of Gnedenka's book, or some pages from Billingsley's book, to get into the technicalities. Okay? But what actually we do, it's a common notation to tackle discrete, continuous, singular, or mixed cases. So we can always write d capital F of x, which will be the sum in the discrete case, f of x dx in the absolutely continuous case, or something else in the mixed case. So I should write that an absolutely continuous case df of x is nothing else but capital F prime of x dx, where capital F prime of x is your PDF little f of x. Okay? Is this understood? Okay. And of course, when we need to find the variance, we have to deal with the other function. So variance of random variable x, which is denoted by sigma squared subcapital X, so just sigma squared is So, and by the way, yes, so Ex is frequently denoted by mu or mu sub Ex if you have more than one variable considered at the same time. So, and variance is integral from negative to positive infinity of x minus mu squared d capital F of x. But since the variance equals the second non-central moment minus the squared expectation, so we frequently evaluate it as integral from negative to positive infinity of x squared df of x minus integral from negative to positive infinity of x df of x squared. Okay? So using Lebesgue-Steltiès integral to evaluate all these functions is challenging, but it would be the time well spent for you. I, for instance, got interested in it just between my freshman and sophomore years. So I read advanced books on functional analysis, and eventually liked it very much, and it helped me in my studies of advanced probability theory. Okay, and also I want to make some comments or repeat and extend some comments which I made at the end of Wednesday's lecture on why this interval 0, 1 is so important. So, so now I want to erase this formula for expectation. Okay. So for Lebesgue, so for Lebesgue's measure on the unit interval, we do a lot, of course, but for a absolutely continuous random variable capital X, its CDF capital F sub capital X sub little x is uniform 0, 1. Therefore, it's if we take the inverse of this one-to-one function, then f capital X negative 1 of uniform 0, 1 random variable will have the distribution coinciding with that of random variable capital X. So it's one-to-one correspondence. So these relationships, of course, they are important in stochastic modeling. So when you simulate random numbers, you usually simulate 0, 1 pseudo-random numbers and then use such a transformation to simulate general random numbers having a particular distribution. Okay? So, therefore, you can switch from Lebesgue measure on unit interval to Lebesgue-Stiltjes measure on the real line. Okay? Now, we should move on and consider two or more dimensions. So, in the case of two or more dimensions, we ought to deal with random vectors. And in B52, you considered the bivariate normal probability density function okay. So okay, so I consider bivariate normal and multinomial distributions. So in Evans and Rosenfeld's book, they considered, just a second. Okay, so now it's references, another page. Okay, so it's here. So for multinomial, it's example 285 on pages 102, 103. For bivariate normal, it's example 279 on pages 89, 90. So, of course, you learned general formulas, but there are two particularly important multivariate distributions discussed in B52 in detail. Say, multinomial distribution occurs when you roll a die several times and observe the number of ones, twos, threes, etc. in n rolls of a balanced or not necessarily balanced die. Okay? So, and bivariate normal distribution is important, so that's how you learn usually the correlation coefficient and so on. I'm not saying that it's easy, but it will be our starting point to consider multivariate normal distribution where we will have to use the matrices. Okay? Sounds exciting, but we will need to invert them and so on. So anyway, let's talk about two dimensions. How to generate probability measures on R squared. So I mentioned about Borel sets on R2, which are generated by particular intervals. So let's consider script b squared. So the first interval for, say, random variable x is I1, which is interval from negative infinity to a, and for random variable y, it's I2, which is interval from negative infinity to b. And we are interested in probability that capital X is less than or equal to a, and the second variable y is less than or equal to b. So we don't usually have to write the intersection sign. Usually we put a comma in lieu of the intersection sign and drop the parentheses. But this is nothing else but the joint CDF of random variables x and y evaluated at 2D point AB. And that's what you were expected to see in B52. Okay? So it's joint CDF of random variables x, y evaluated at point AB from R squared. And then these joint CDFs have particular properties which are nice, but unfortunately not that nice as in the one-dimensional case. So when you probably looked at these properties, so they most likely appeared to be too boring for you. But they're, of course, important, and these properties follow from properties of probability measures on R squared. So I'm, of course, talking about the continuous case. And then you consider non-random function, say little g of x, y, and so actually it could be a non-random function of arguments little x and little y, and then you plug in capital X for little x, capital Y for little y, and then g of capital X, capital Y is a new random variable. So in order to find its expectation, of course, it's possible to find the probability law of this new univariate random variable first. But the other approach is to find the double integral over R squared of little g of little xy df xy of little x, little y, which is going to be Lebesgue-Stiltjes integral on R squared. So it is defined as the limit of the integral sums, which is not the most exciting and actually quite a boring topic, but that's how all the definitions work in analysis as well as in the advanced probability theory. Fortunately, there are shortcuts in calculus, analysis, and probability theory. Yeah.
Is that expectation of Gx, big X?
Yeah, it's capital Y. Yeah, it's a good point. It's a capital Y. Little x and y are for non-random arguments. Capitals are for random variables. Okay. Thank you. So of course, if you have more than two variables, and we are going to consider such sets, so we'll have to deal with antipole integrals. Triple integrals is just something pretty simple. So, say, for comparison, in my PhD thesis, actually I had to deal with integrals of increasing dimension pertaining to more and more random variables, so I had to get some recursive relations. So such things happen. You cannot anticipate how many dimensions you would have to deal with. You probably heard about reducing dimension techniques, about dimension curves, etc. These are hot topics, but not really for this particular course, although they're very important. The number of random variables to be considered simultaneously can be pretty large, and it's certainly a hope to figure out the most important of those and try to skip the other ones. So it's frequently done in statistics. Okay? So, but let's talk about shortcuts, which you, of course, know. So, in the absolutely continuous case, we use the fact that the second mixed derivative of the joint CDF, capital F, with respect to x and y is denoted by little f sub capital XY of little x, little y, and it's called the joint PDF. And therefore, this integral can be evaluated as this joint PDF, little f sub capital X, capital Y, of little x, little y, dx, dy. Yeah, and you know from calculus that in nice cases you can switch the order of the integration with respect to x and with respect to y, yeah? So there is such a nice Clairaut theorem which doesn't always work, but in good cases it does work. So it's a nice shortcut, and of course you know that in the independent case the joint PDF can be factored into the product of marginal PDFs. Yeah? So it makes things even simpler. Okay. So this is true in the absolutely continuous case. But in the purely discrete case, this is going to be P of xy, and you get double summation of little g of xy times joint PMF of our random variables, which are assumed to be discrete, and P of xy, of course, little p of xy is defined as the joint probability that the first variable, capital X, takes on the value little x, and the second variable, capital Y, takes on the value little y, where again comma is recognized as the intersection. Okay? But these are just two special cases. And they are not always fulfilled. I would rather say that it's a piece of luck if you deal with purely discrete or purely absolutely continuous case. If you get independence on top of them, then you're a happy person. A problem could be solved reasonably easily. Usually, this is not the case. Is it clear? You know, when I studied this kind of stuff, learning a relationship, say, between moment-generating functions and probability density functions, I learned and used classical stuff. But then when I started doing research in probability theory, I realized that for some, or for quite a few distributions, all these nice theorems, which I learned in advanced probability courses, they just fail to be applicable because the conditions simply are not fulfilled. Okay? So, therefore, be aware of this. What you learn on B52 is a kind of the ideal world. It's a good starting point, though. And I want to talk about real-life distributions, those which I worked with my co-authors just less than a decade or about a decade ago, which are important models of property and casualty insurance or non-life insurance. And there is a methodological reason why I want to talk about such models for a few minutes. So your random variable, capital X, is a Poisson random sum where the summation index is also random, so you get two kinds of randomness. But then what you do, you add up gamma random variables, which are ID random variables with common gamma distribution. And gamma i's and Poisson are also assumed to be independent. And let me say a few words on where such random variables occur. So you heard that if you consider a particular time period, say a week, then the number of accidents in GTA area on 401 would be Poisson distributed. So you were expected to learn about various applications of the Poisson model. There are many others on top of insurance, say Poisson model, as the distribution of the spread of solar energy on the surface of the sun, the phenomenon known in astrophysics as intermittency. So there are such kinds of applications. But for insurance purposes, it's just the number of accidents. Okay? Now, what would be the claim amount? Say, some accidents are not reported, but we will talk about what to do with some accidents not being reported later on when considering stochastic processes. So assume that each accident is reported. We have their Poisson number. And the amount per claim is usually modeled by gamma random variable. So exponential variable is not sufficient, because if there are multiple vehicle accidents, say for each car it would be exponential damage or exponentially distributed damage. If you have the sum of two or more exponential random variables, so you get a gamma random variable. Understood? But it's a major stochastic model of property and casualty insurance. So here you actually have two sources of randomness, and you consider a discrete Poisson and absolutely continuous gamma random variable together. But the real life makes us consider such models. And finding the distribution of such a random sum was a rather challenging problem. And I solved it with my co-authors, and it got published in 20. Actually, it was published in several issues of a journal in 2012, 2013, and 2014. And the result was somewhat similar to what you learned in first lecture on zero-modified exponential model, that you have point mass at zero, and you have the density component for positive half-line. But the density component for zero-modified exponential was just exponential function. Yeah? So here for this variable, the density component has a rather complicated form expressed in terms of special functions of analysis. But still, it's doable with a lot of effort, with experts from several fields of math working together. Actually, even here, you see that the dimension is not necessarily 2. You don't even know how many gamma variables you would have to consider. So therefore, dealing with multivariate random variables is what life and applications necessitate. Multivariate normal distribution is particularly stressed on the course syllabus. Okay? So you know a special case which we will review pretty soon, but not today. But at the end of today's lecture, I want to talk about an apple from the same apple tree as the bivariate normal distribution, which is not that well known. So it's an apple. From the same. So I have two random variables, x and y, with the CDFs, capital F sub capital X of little x and capital F sub capital Y of little y. And I introduce the joint, or I would say, I introduce a certain joint CDF as follows. Capital F of xy is defined as F, so let it be F1 and F2. F1 and F2. So it will be capital F1 of x times capital F2 of y times the figure bracket of 1 minus alpha times 1 minus capital F1 of little x times 1 minus capital F2 of little y, where fixed alpha is from the closed interval from negative to positive 1. Then it's going to be a certain joint CDF. So it's going to satisfy the properties of a joint CDF. And moreover, such an approach can be used recursively. So we can generate multivariate CDFs in higher dimensions. And what actually happens is that in the absolutely continuous case where f1 of x and f2 of x are both exponential with mean 1, little f of xy, which is the second mixed partial derivative of the joint CDF x with respect to xy, is going to be equal to 1 minus alpha times 1 minus e to negative 2x times 1 minus e to negative 2y e to negative x minus y for x and y being non-negative, and it's going to be equal to 0 otherwise. So one example of such a construction of joint CDFs is obtained when both these original CDFs are exponential with mean 1. And in this case, the joint PDF exists, and it is expressed in a neat form where alpha is closely related to the correlation coefficient. So I need to finish now. Thank you, and I will see you on Wednesday. Okay?